Welcome to the course on audio signal processing for music applications. In the previous demonstration lecture of this week, we talked about the sinusoidal model from a practical perspective. So we analyzed some sounds, some simple sounds, and we tried to figure out what parameters from the sinusoidal model would give us a good visualization and resynthesis of the sound. So I want to complicate it a little bit more by choosing a little bit more complex sound. So we are going to analyze the mridangam. The mridangam is an instrument, a percussive instrument from the south of India that is played as part of the Carnatic music tradition. And in this picture, in fact, we seeing Ajay on the mridangam, and he's a TA of this course. And in the voice singing is Vignesh, which also is a collaborator in our group, and we are also going to be analyzing some of his sounds. So let's go find some mridanga sounds, and of course what we would do is go into free sound. So if we look for mridangam in a free sound, well, we're going to see, well, there's quite a few sounds. There is 7,000 sounds of the mridangam. That's pretty good. And the first one, let's maybe just open this first one. And in fact, it's a sound that was uploaded by Ajay, and we can listen to it. Okay, that's pretty nice. The mridangam is a very interesting instrument. It produces quite a few different qualities of sound, the way the instrument is hit, and there's different balls that are called to produce different sound qualities. And rhythmically, it's really complex. I mean, it's the music of the Carnatic music tradition, and the way that the mridangam is played. It explores very sophisticated and complex rhythmic structures. Let's just use one of these sounds. In fact, as part of the package, the sound that we are using for this class, there is a sound by Ajay, and in fact it's this fragment here, and we can also listen for that one. Okay, so this is the sound, and we can play it. Okay, so let's analyze this sound by Ajay. Let's open the SMS Tools GUI, and let's start by looking at the short time Fourier transform. So we'll go and get a mono version of this sound, the mridanga sound. Okay, and we have to decide what parameters to use. So before we can really make any decision, let's just take some default kind of parameters. For example, let's use a humming window. That's kind of a default window that works quite well. In terms of the window size, okay, we don't know much, but okay, let's start with 1,000 samples of the window. The FFT size, when we don't know much about it, the bigger the better, if it is not take too long. So okay, so 4096 seems like a good enough number. And the hop size, well, it's good that is the smallest possible, because a percussive instrument with these sharp attacks, it's good that we have a lot of frames and we can have quite a decent time resolution. So let's compute this. Okay, so this is the result. The output should be the same, because we haven't done, it's the same. We haven't done much to it, and the hop size is a good. It's in a good relation with the window size. And now, what basically we'd like to is understand a little bit the sound, so that we can better choose the parameters. So let's think about the window size that best fits this sound. So by for doing that, let's zoom into one of these sounds. For example, this one looks good because it has a lot of horizontal lines. Okay, so these are the partials of a sound. No, it's a membrane that creates some vibrations. They may not be completely harmonic, but clearly there are some very stable partials of a sound of the resonance of the instrument, and we would like to see what is the minimum distance between two partials, so that we can decide what is the resolution that we need, the best resolution that we need. Okay, and by looking here on where the cursor is, we can see, for example, that this first horizontal line is around 200 hertz, and the second one is around 400 hertz. Okay, so that means that according to these, at least the minimum distance between two consecutive partials is around 200 hertz. Okay, so from that we can try to compute an appropriate window size. As we said in theory class, we have to start with the number of beams of a window. So let's start with like this Hamming window. So it's 4 beams, and let's multiply by the sampling rate, 44,100, and divide it by the frequency resolution we want to have. In this case, we make a guess of 200 hertz that we identified as a distance that was present in these sounds. Okay, so this is 882 samples. Okay, so we would need these 881, or let's say 83 samples, so that we have a frequency that is an odd frequency size. Let's still keep the FFT size big, so there's no harm on that. And in terms of the hop size, well, it looks like we can have a smaller one. So let's see, 220, that would be 1/4 of that. Okay, and let's compute it. That's not that different from what we started. So in fact, what we started was pretty good. Okay, so this is the kind of an analysis that should be okay according to this measure. Now let's analyze the sound using the sinusoidal model. So let's go to the interface and let's open the sine model. So let's go for the Madranga sound. Okay, and well, we have to choose the parameters for that. So let's use the same ones. So we have these 800, around 883 samples. Let's use the same, the Hamming window. The FFT size, let's leave it to this 4096. Magnitude threshold, maybe we do not need that much, let's say -60. Duration, well, let's make sure that we have good enough track, so let's maybe 0.05. Number of sinusoids 150, yeah, we need quite a bit. Deviation doesn't deviate that much, the sinusoids in this type of sound, so this would be okay. Let's just first try this one. Let's see what we get. Wow, not that much. Okay, so we have analyzed the sound and we obtain very few sinusoids, and if we listen to the result, well, not much there. It has some sound, but not much. So what can we improve from this? Well, the window size, I guess it was all right. Clearly, the magnitude threshold could be lower because clearly this sound was not recorded very loud, and a lot of these things, especially during the decays, is quite soft. And clearly, the sinusoidal tracks could be shorter because the strokes are very short, and some of these trajectories are going to be very short. So let's have it at 0.01. Let's just have the rest as it is. Okay, that's better. That's better. Of course, from this picture, we might not get a good idea because we don't see the amplitude of each of these, but that gives you something. And clearly on the waveform, it's pretty good, much better. Let's listen to that. Yeah, that's pretty good. That's pretty good. Of course, one basic problem is the frequency resolution and the time resolution, this time frequency compromise. So let's see if we can get better frequency resolution. So these harmonics I am sure there are some, as we can see here, that are closer together. These are partials, are not harmonic in fact. So some are related harmonically because in the resonance of the instrument emphasizes certain harmonics, but some are not completely. So let's try to make it bigger windows so that we can capture partials that might be closer together. So for example, let's go to 3001 samples, so quite a bit more. See what happens. Okay, and let's just leave the rest untouched, and let's compute it. Okay, interesting. So we definitely got many more lines, but looking at the waveform, it doesn't look too good. Let's listen to that. So in fact, if you pay attention, one of the biggest difference is that now the attacks are not crisp. They're kind of smeared. We can see also here in the waveform that the attacks are not so good. So okay, so that was not a good idea. We might have gained on frequency resolution, but we definitely lost in time resolution. So let's go back to a number that is maybe, okay, let's have 1,000, which was kind of a compromise. See what's happening now. And okay, that's pretty good. That's looking at the waveform, it looks quite decent. And if we listen to that, okay, it's pretty good. Even though if you listen carefully, we are still missing a little bit of the sound. The sound, especially during the attacks, there is a lot of energy. There is a lot of noise into that maybe with these sinusoids are not well captured. But that's one of the things that we'll talk about and we'll learn how to handle in the next few classes. This is all I wanted to say in this lecture. So let's go back to the slides. So we have done a little bit of more analysis of a particular sound, in this case the madranga, using the sinusoidal model. And of course we have used the SMS tools and sounds from Freesound. Hopefully this has given you a better understanding of the sinusoidal model, and at the same time maybe you have discovered this new fascinating instrument, which is the madrangam, and which I encourage you to listen to it, and especially in the context of Carnatic music. So this is all, and I will see you next class. Thank you very much.